Okay, so one thing we didn't get to last time is this notion of um, floor or ceiling. And the um, so the book has this like few paragraphs at the end of the section, where we say that the floor of any number, any real number, let's call it X, is where we truncate it. And so this is like fairly intuitive. So we write the floor of X. So floor of X with these, it's like we wrote a square bracket, but we just take off the bracket part at the top. So we have the bracket part at the bottom. That's the floor. And there's also the bracket part at the top, and that's the ceiling. And so my examples for you are, for example, let's say we have the number 2.9. For the floor, we basically round down. So we just truncate any decimal that's there. And so the floor of 2.9 is 2. The floor of pi is 3.14159,265, and so on. And so if we just cut off the decimal, that gives us 3. The floor of negative 4.2. So if we cut off the decimal, then we get negative 4. But if we look on the number line, so let's say this is negative 4, negative 3, negative 5. So if we're at 4 point, and let's just say that's 4.2. If we truncate the decimal, does that give us what we want? No, because we're supposed to round down. And so for a negative number, truncating the decimal actually rounds us up. So if we're computing the floor of a negative number, we have to subtract 1. So I'll say we subtract 1 if X is less than 0. One of the questions that they ask is, consider the problem of finding the number of multiples of 7. So how many multiples of 7 between 1 and 100? So we could go through and we could count them all, but I don't like the sound of that. So the other way is to do division, where we divide 100 by 7. And if we do this long division style, 7 goes into 10 once, remainder 3. 7 goes into 30 4. When I get up here, it becomes impossible to do mental math. So that's 28, right? Remainder 2. And so that's 14 point something. And so if we cut off, then the floor of that is going to be 14. So that gives us our answer. And then the counterpart to that is the ceiling, where we round up. And so this is for floor. And so for ceiling, for the ceiling of negative 4.2 is where we do just truncate the decimal and we just leave it, right? So that's fairly self-explanatory, but that's part of your homework, so I wanted to make sure we touched on it. Any questions on that? Great. Okay, now we get to talk about even and odd numbers. I've been excited for this all week. So I want you to think for a second. We'll do this think pair share style. So think, what's an even number? Or what's an odd number? What are some examples of even and odd numbers? How do we write them? If you already know the answer, sit tight. But think for a second. What's an even number? Okay, turn to your neighbor and share. What's an even number? What's an odd number? All right, what's an even number? Let's share now. What's an even number? What are some examples of even numbers? This is the duh part of the semester. Yeah. Two is an even number. That's my eraser. Two is an even number. Give me another one. Eight's an even number. Um, four is an even number. What's an odd number? Three. Seven's an odd number. 251 is an odd number, right? Again, duh. But what makes a number even? Yeah. Yeah. Okay. So we as mathematicians are going to write any even number. We're going to claim the authority to write any even number as being divisible by 2. And so that means we want to write 2, and we're going to introduce letters into this. So we want to write 2 as a product of 2, which is 2 times 1, right? 2 times 1 is 2. We can write 4 as 2 times 2. We can write 8 as 2 times 4. Let's see. In my notes, I have 1928. 1928 divided by 2 is 964. And we can go on, right? So the idea is that we have an even number as 2 times k, where k is any integer. So this is my shorthand to say that k is any integer. Remember, this is how we write the set of integers, and this is saying that this element is in that set. So k is in the set of integers. So this is how we're going to write an even number. It's just 2 times whatever. Out of curiosity, what's 0? Is 0 even or odd? Who votes that it's odd? No votes. Great job. Who votes that it's even? Great. Okay, so let's that's a statement. Let's prove it. Um, 0 is even. Let's write a proof. So, okay, I didn't plan this beforehand. I think I want to prove it by contradiction, but in order to prove it by contradiction, I have to say that 0 is an odd number, and we don't know how to write odd numbers yet. So we're going to talk about odd numbers first, and then we're going to prove that 0 is even. To be continued. Okay, so when we write an even number like this, when we write it in the form of 2 times k, we can prove stuff. And so we're going to start with the proof that any sum of even integers is even. And so when we say this, we know what the form of an even number looks like. It's 2 times something. And so we're going to take 2 even numbers. We don't know what they are. We're just assuming we have any 2 even numbers. And we're going to add them together and look for something that's still in this format, 2 times something. That's what we're looking for. So let's say we've got 2 times x. That's the first even number. Maybe let's call it a. And our second even number is 2 times y. X and y we can assume are both integers. They don't necessarily have to be the same thing. They can be something different. So we've just chosen 2 numbers, and we said they're even because that's what we said right here. And we're going to add them together. So to do a plus b, that gives us 2x plus 2y. And so that may seem okay, but there's a 2 in both terms. So we can factor that out. So, and that's by the, what property is that? Distributive law that we talked about last time. So by the distributive law, that's property 4. We get 2 times x plus y. Are we done? Did we get this answer, a plus b, in a form that looks like 2 times something? Yeah, there's the 2, there's the something. We did it. So as mathematicians, we tend to start our proofs with the word proof. So on the board, I'll probably write it and underline it. And then we end with either a little square or QED, which stands for something in Latin that basically means I've proved it. Great. So now we just proved that any sum of even integers is even. So this will hold for any integer, no matter how big. It's always going to be even. Okay. You remember last time we talked about rational numbers? What's a rational number? What do you remember? Yeah.
Express it like one integer over another integer.
Mm-hmm. So we wrote it as something like m over n, where m and n are both integers. Right. So we're going to talk about divisibility, where for divisibility, let's say we have two integers, a and b, and I think the book is like at the beginning of, what is it, 2.2? They say that any letters that we use going forward, unless otherwise specified, are going to be integers. So maybe we'll adopt that as well. So if I use a letter, unless I say it's something else, then we'll assume that it's an integer. So these are both integers. And let's also assume that b is not 0, so we don't break math. So we want to say if there is a integer, let's call it q, such that we can write it like a equals b times q, then we can say that b divides a, or a is divisible by b. And we can write it as b and then that's the pipe character on your keyboard, which is above the return key if you press shift. And we write it b pipe character a. And the way we read this is we say b divides a. So if there's some number q that we can have in this formula, then we can say b divides a. All right, that's technical. Let's talk about an example. So consider -15 and 5. We can divide 5 into 15, right? And -15. So we know that 5 times -3 is equal to 15. And so in this case, or 5 times -3 is -15. In this case, 15 is A, 5 is B, -3 is Q. And so we can write that 5 divides -15. If we say, let's consider 20 and 2. Turn to your neighbor. What's A in this situation? What's B? And what's Q? And when you write it, something divides something. What is it? Turn to your neighbor. Talk about it. All right, what's A? Just call it out. 20. What's B? What's Q? 10. Exactly. Great job. And so when we write it left to right, what goes in the left spot? What goes in the right spot? Right. So we can say that 2 divides 20. And so this is where we get our notion of what's an odd number. Because if we take, for example, 2 and 21, can we write so let's see. In this case, A is 21 and B is 2 and there's some number Q. Can we find some number Q that works for this? This is where our assumptions come into play. Because we've assumed back here that going forward, all of our numbers are going to be integers. So A and B are integers. Q is also an integer. And so we know that like 7.5. Wait, no. I can't do math when I get up here. 10 and a half. 2 times 10 and a half gives us 21. 10 and a half is not an integer. And so there's no Q that's going to give us a satisfying solution to this equation. And so that's how we know that 21 is not an even number because 2 doesn't divide it. So the way that we write odd numbers then is going to be, so I have an answer, but maybe I want you to talk to your neighbor and think how could we represent an odd number this way? Take 20 seconds, turn and talk about it. All right, what do you think? So if we write even as something like 2 times k, how do we write an odd number? I know I heard at least one correct answer. Yeah. 2k plus 1. 2k plus 1. Yeah. So that's how we write an odd number, where we know that any odd number is 1 more than an even number. We just know that from like 2, 3, 4, 5, 6. They alternate. And so we take any even number, we add 1, we get an odd number. And so what is 21 in terms of this format? Yeah.
Times
2 times 10 plus 1. Great. What about, let's see, I have 1921 in my notes. Half of 1920 is 960. And so 2 times 960 plus 1 gives us 1921. So we can do this where you can get if you subtract 1 divided by 2, you can write any odd number in this format. Okay, so now let's prove that 0 is even. So maybe So I think the easiest way to prove something like this is to assume that it's not true. We saw this a lot in the properties last time. So let's say, suppose 0 is odd. So we're making a completely contrary assumption to what we're trying to prove. We're gonna suppose that the opposite is true, then we're gonna work through the consequences of that and eventually get to the point where we say, no, actually, that's crazy. Our original assumption was correct. So we suppose 0 is odd. What does that mean we can do? We can write it as an odd number. So 0 is equal to 2k plus 1, where k is an integer. So if we write it that way, then I suppose we want to find out what k is. So we'll move 1 to the other side. So we have -1 is equal to 2k. And then we've got a 2 still over there. So let's divide everything by 2. So we get k is -1 over 2. Is this a problem? Yeah? Why? Sure. Yeah, so we said k is an integer. That's not an integer. So we have reached a contradiction. So as you're getting started, to me, this seems to flow fairly straightforwardly. So maybe we add k is not integer. And then we say, that's a contradiction. Therefore, 0 is even. QED. So this is how we want to prove things. So we don't want to prove things by, like so let's take the first example of prove the sum of any two even numbers is even. The way you don't prove that is by giving me 42 and 962, or let's say 8. Use a different number. The way to not prove the sum of any two even numbers is even is to give me two even numbers and say, here's their sum. That's even. It's a nice example, but in this class, we're going to really be talking about how to prove things not just for one case, so for these two numbers, but in general. So I want to know that any two even numbers, these are just two examples of even numbers. I want to show that any even number sum is even. So keep that in mind as we go forward. Okay, how are we doing on time? We got half an hour left. All right, so any questions on even numbers or odd numbers before we go forward? Great. Let's briefly talk about, I'm not 100% sure that's the word that we use, but I think it is. Let's talk about primality. So the notion of prime and composite numbers. Again, this is something that you have learned. You know what a prime number is. It's something that's divisible only by 1 and itself. And composite number is basically anything else. So officially, we say, let's say some number p, again, we're going to assume it's an integer, is prime if it's only divisible by, the book has plus or minus 1 and itself. They also have plus or minus p, which, sure, I guess. That's just a -1, which, yeah. But the same idea holds, where it's only prime if it's divisible by 1 and itself. So now that we know the term divisor, which means evenly dividing, so if there's more than two divisors, then it's, I will box that one, and then it's composite. So those are the terms that we use. And that means that, so let's say X is our, no, let's stick with P. So P is equal to A, let's call it A and Q. And so if there's sorry, this made sense in my head, but I don't know how to put it into words. If there's more than one divisor, so we say that did I define divisor? Did I miss that? I did. Sorry about that. Okay, so some notes to add to this point is that A is a multiple of B. So we can add B so many times and get A. And we can also say that B is the divisor of A. So B divides A, B is a divisor. And then Q is the quotient. So that's for like if we divide 5 into -15, the quotient is -3. So these are also terms that you learned when doing division in grade school. But these are also the terms that we'll use now. So let's see, going back here. So if we've got P, then A is going to be, in this case, A is going to be the divisor of P. And if we can add A so many times, if there's more than one A other than just one and P itself, then we say that P is not prime, it's composite. Okay. Let's see. Now I think it's time for activities. So let me pull that up. So we're going to do theorem 2.4 in the book. It's on page 15. And so these are proofs like, page 15. These are proofs like the sum of any two even integers is an even integer. We did that. Sum of any two odd integers is an even integer. So what I'm going to do is I'll have you work with your neighbors. I've got whiteboard markers if you want to throw your solution up on the board, and then we'll talk about it. So I'll come around and give markers, and I'll come tell you which one to work on. And then once you're done with that, you can choose the others to work on. All right, thank you for playing. Some things that I want to touch on from what I saw. So I noticed at least, so I think you guys did one of the proofs for where you proved it by contradiction. And there's another group who proved it where they just said, this looks like an odd number, or this looks like an even number. Therefore, we're done. So this is the sort of thing where I said this to a few groups. There is a right answer in this class where we have to be able to prove a statement logically. But there's multiple answers in the sense that we can get there in a convincing way using different kinds of arguments, right? So in seminar, if you're trying to prove a statement, you can argue, you can maybe go one way or you can go the other way. And the same sort of thing holds true here, where you can, if you prove it by contradiction, and that's the style of proof that makes sense to you and you're able to logically reach that conclusion, great. If you are reasoning through it and you say, I'm trying to prove this thing is odd, and then I get to something that looks odd, and then I'm like, great, we proved it. That's also correct. So for these, I would say maybe this makes more sense to me to just be able to say, that looks odd, we're done. But if you proved it by contradiction, that's also correct. So I just wanted to make sure. So because I know a lot of people are like, math doesn't have one right answer anymore, where the right answer is developing a logical and convincing argument. That's what we're doing. And so there's multiple ways to get there. Another thing I saw is that I think the group in the back was proving number 5 by, so number 5 is the product of an even integer and any other integer is even. And so what one group did was you looked at even times odd and then even times even. And the other group over here did even times any, where they just didn't write it in the form of an even or an odd number, and then found out that it looks even. Whereas this case, they proved that each one looks even. Again, two different ways to get the same result. So the step on the right may look cleaner, but if you want to be thorough about it, maybe you wanted to prove like for sure that a number is either even or odd. So therefore, let's test it when it's odd, test it when it's even. So this is proof by cases, and then this is a more general approach. So again, two different ways to get to the same place. All right, we've got about 3 minutes. So we've got these. I might have us do some of these next time. I want to briefly talk about, so the other thing is that the answers for this proof for 2.5 are in the book. So go take a look at that, and then we'll come back on Monday and maybe talk about a few of them. I do want to briefly talk about the example, which is, so their example 1, which is on page 16 of the book, which is where we take any 2-digit integer and so take a 2-digit integer, switch the digits, subtract the obtained number from the original one, and prove that the difference will always be divisible by 9. This is one of those like math magic tricks that you see when you're a kid and you're like, okay, like that's cool, but it makes my head hurt and I don't know why. We're going to talk about why. So take 2-digit integer, swap digits, and then subtract old minus new. That number is divisible by 9. So I'll write out the steps for kind of how we get there. So let's have the old be n, and we can write that as it's got digits a and b. The new is m. So we write it as 10a plus b because we live in base 10. So like 20 is 10 times 1 plus 0. So it's just writing that number in a different format because the second digit is multiplied by 10. And so for m, we just swap a and b. So we've got 10b plus a. And so then we do n minus m. And then I will write the result, which is 9a minus 9b, which is we subtract the two. And then I hope you can see that that's divisible by 9. So that's how we get that. So we're out of time. Next time we will go over a little bit of the theorem 4.3, 2.5. I'm wrong. You can start on the homework. There is some examples on floor, ceiling, divisibility. So get started on that. It's due next Friday. And have a good weekend. Happy first week of school. We did it.